GMAT all day!
To start off this next video on overlapping sets, I want to just revisit for a second the table that we used in the previous problem, and I want to use it to illustrate just a point about how I set up my overlapping set questions. And so one thing that I always want to do when setting my overlapping set questions up this way is I want to make sure that the number or the expression that I put within each of my boxes represents the actual number of people or things that are in that group. So, for example, what I would not want to do is if they had said in the previous problem that 30% of my participants were females that had an increased risk of cancer. What I wouldn't want to do is just put something like this into the box here. Because remember, the goal is not to just fill in the table. The goal is to make equations, to organize your information in the table so that you can use it to make equations that you can then use to solve for whatever you are looking for. I cannot take this 30% here and just plug that into an equation because it doesn't really represent anything. Even worse would be you just put something like this, because this is not only confusing, but it's outright deceptive. 30% is not equal to 30. And so in that case, what you would want to do is you would have to say, okay, so if 30% of my study participants are females that are at increased cancer risk, that means I have some number of total people that is in my study, and I'll call them T, and I'll put them here because that box represents the total people in the study, and therefore 0.3T of my participants, or 30% of T of my participants are females that are at increased risk for cancer. And even though this might be less satisfying than putting an actual number into this box, it is a more accurate representation. In fact, it's the only accurate representation that you could fill in, at least if that's the only information you knew so far. Now, the one exception to that rule is if all of the information that you are given in your prompt, or if it's a data sufficiency question, it would include both the prompt and your statements. If all of the information given is either percentages or ratios or just fractions, if that, in that case, all that matters is the proportion that relates everything together. Everything is just sort of relative to everything else, and so maintaining that proportion is all that matters. And therefore, you can just assume that your study has 100 people, for example, and therefore, when they say 30% of your of your patients are females who are at increased cancer risk, you can just put a 30 here, because all that matters is that your proportion is maintained, and 30 over 100 is 30%. The thing to keep in mind with this is if at any point they give you a discrete number, well, that will throw everything off, because once they throw in a discrete number of any kind, everything is no longer just relative to everything else. Everything is sort of anchored to that number. So if in the prompt, for example, if it's a data sufficiency question, then the prompt gives you all percentages, and then the first statement gives you some more percentages, but then in the second statement, they say 10 people in the group are males that are not at increased risk for cancer. So once they give you that number 10, everything is no longer just relative to everything else. Everything is sort of anchored to this 10, and you cannot make any of those assumptions anymore. So let's take a look now at an overlapping set problem where everything is given in terms of all percentages, and we can make those assumptions. So 55% of employees at Initech drink coffee in the morning. Of the employees who do not drink coffee in the morning, 2/3 also do not eat a bagel. If the number of employees at Initech who drink coffee in the morning without eating a bagel is 1/2 the number who eat a bagel without drinking coffee, what percent of Initech employees eat a bagel in the morning? So first step in any overlapping set question is identifying that you have an overlapping set scenario, and we have that here. We have two groups of people. We have coffee drinkers, and we have our bagel eaters. And everybody at Initech has two options. They either are coffee drinkers or they are not coffee drinkers. And everybody is either is a bagel eater or not a bagel eater. And then I notice, so all of the data points that they give us are either percents or fractions. That means all we care about is just having things in the right proportion. So I'm just going to assume we have 100 employees at Initech. And note that even our question is asking for a percent. And so even the question needs to hold up as a percent. If the question said how many employees at Initech eat a bagel in the morning, then that would throw off all of our assumptions. So I'm going to assume we have 100 people at Initech. And now let's fill in our table based on this. So 55% of the employees drink coffee in the morning. So that's my total coffee drinkers. That's this box here. Let's say we got 55 people here, which means we got 45 people who are not coffee drinkers. Of the employees who do not drink coffee in the morning, we only care about these 45 employees here. Of those 45 people, 2/3 also do not eat a bagel. So that would mean this box here, no coffee, no bagel, is 2/3 of my no coffee people, 2/3 of 45. So this is 45 over 3 is 15, so this is just 30 people in this box, and so that means 15 people have a bagel with no coffee. If the number of employees at Inatech who drink coffee in the morning without eating a bagel, so coffee, no bagel, is 1/2 the number who eat a bagel without drinking coffee. So that's 1/2 of this number here. And so this is where you can get into a little bit of trouble sometimes when you make this assumption, is you can end up with fluky scenarios where, for example, you have partial people. Don't worry if that happens. It does not necessarily mean you made a mistake. It's okay, because remember, these numbers are numbers we just made up. All that matters is that everything is in the correct proportion. So the fact that 1/2 of these 15 people fit into this group, coffee with coffee with no bagel, is 1/2 of 15, which is 7.5 people. Well, that's okay, because that's not the actual number of people. It's not like we have people with partial limbs drinking coffee without a bagel. We just made up this number here, and so you can get somewhat fluky numbers sometimes. And sometimes if you want all integers, you can choose a different number here. You can choose a number other than 100. So maybe if we chose a multiple of 3 or a multiple of 5 or something, things would have worked out better. But like I said, this number is not too terrible as long as it doesn't freak you out. So we got 7.5 people here. Based on this, it looks like we can fill in our entire chart. So that is the dream scenario. That is not the goal of an overlapping set problem. The goal isn't to fill in the entire chart. The goal is just to fill in whatever information they give you. But if you can't fill in the entire chart, that's the dream scenario. So we have 37.5 people who are non-bagel eaters, which means we have 62.5 people here. And therefore, 55 minus 75, 7.5 is what? 55 minus 7 is 48, so 47.5. This looks like everything adds up. And so we filled in our entire table. And so then we just got to look at, make sure we fill in, we answer the question with the proper box. So what percent of Inatech employees eat a bagel in the morning? So now if you choose the wrong box and fill in the wrong answer, I can't help you. So that is this box here, right? My total bagel eaters is 62.5% of my employees. If this number here was not 100, you would have to calculate what that actual percentage is. So if you chose 300 people, you'd have to find out what 62.5 over 300 is. And that would change your answer. So here, because we had all percentages though, we could fill in these numbers here just as if it were the actual number of people in that group. At 62.5 C. So next we'll take a look at a percent question where they mix both percentages with discrete values.